Okay. So here I have a list of some of the theorems that we're going to use in this first section. Okay. We need to know these theorems that I've given you, and we want to kind of know where they come from. I'm not going to take the time because I don't have the time right now to write out the formal proofs. I will assign a couple of these for you to do on homework, but we will walk through them and talk about how we can write a proof out on each of these to make sense of them. Okay. So theorem 8.1 says, in a circle, congruent central angles have congruent chords. Okay. And there's a picture drawn here, but I'm going to draw another picture just to kind of construct it for us. So if you have a circle, given center, here, say we had circle O. If I have congruent central angles, so I'm going to pick a couple points over here, A and B, and central angle is, by definition, it's the angle that's formed at the center of your circle, is the vertex, and you have two radii here, right? So this angle right here, and I'm going to draw another central angle that's congruent to it. I'll put it over here, point C and D. All right, so that's our given. We have two central angles that are congruent. And if you have that, what we'd like to say or be able to prove is that, well, the chord AB, or the distance from A to B, is the same as the distance between C and D. All right? So let's work on verbal proofs. We're not going to, again, I'm not going to take the time right now to write out a standard proof, but can you see why AB and CD would have to be congruent to each other? Yeah. Yeah, so we're going to have to put some more markings on this picture, right? So what would you have to say? Why? Well, yeah, you're looking at the picture, but when you look at the givens, just look at the givens and over here on the proof. So we don't know that all those are the same, but yes, they are the same. What would be the reason? Why could I put all four of these are congruent to each other? They're all radii. And by the definition of a radii, or definition of a circle, is all these points are the same distance from the center of that circle. So really, the definition of a circle, set from the definition of a circle, all four of those points are the same distance from the center, which is the distance of their radius. Okay. Okay. We're still working towards proving that AB is congruent to CD. So then where do we go? Yeah. Triangle AOB would be congruent to triangle COD. Why? Yeah. And then we get this right here by CPCTC. Right? Now again, we didn't write out the formal proof, but we see it, right? We've verbalized why that's true. And it comes back to our triangle proofs that we are doing back in Unit 3. But this is a statement we need to know about circles. We have congruent central angles, we have congruent chords. The next one is the converse. If you have congruent chords, then you have congruent central angles, right? So if I start with a circle with a center O, and I have a chord over here, AB, and I have a chord, let's say up here, CD, and I tell you that those lengths are the same. That's the given. If that's true, then the central angles that intercept those chords, so this angle right here, COD, and the angle AOB, those two angles, we can prove that those two angles have to be congruent. All right, so how do we get from our givens to what we're trying to prove? What else would we have to state? Yeah, AO is congruent to BO, is congruent to CO, is congruent to DO, because they're all radii, because all those points on the circle are equidistant from the center of the circle. That's the definition of the circle again. And so we can say that those two triangles are congruent. So triangle AOB is congruent to triangle CDO. Actually, gotta say it right. COD. Why? See a hand. Side, side, side. Congruence. Good. And so then we can get that those two central angles are congruent by what? Corresponding parts of congruent triangles are congruent. Good. Okay. So these are not difficult proofs. And you see the usefulness of those triangle proofs to help us with this. Okay. All right. Another theorem we need to know is that if we have a diameter that's perpendicular to a chord, and it then it's going to bisect that chord. Okay. Again, I'll draw a little picture here. So it starts off with some diameter, COD. Remember, a diameter is a chord that goes through the center of the circle. Center's O here, and here's C, and here's D. And let's say it intersects a chord. It's perpendicular to a chord. Okay, so we have this chord AB here, and these are perpendicular to each other. So that's the given. That picture right there is what we have. And we'd like to say, well, here's my A and here's my B, and the part where they are perpendicular is at point E. So we'd like to say, well, if that's true, then the distance from A to E is the same as the distance from B to E. That diameter bisects the chord. Okay. And we're going to use triangles again. And so we end up looking at these two triangles. And we'd like to, if we could show that those two triangles are congruent, then we can show that those parts of the triangle are also congruent. And so we'd like to build that triangle proof. And so what can we say? In order to get, I want to get triangle AOE congruent to triangle BOE. We need to have some evidence of why that's true. And so help me build some evidence. Elena? AO is congruent to what? Oh, EO is congruent to what? All right, so we know EO is congruent to itself. What would the reason be, Lena? That's the reflexive property of congruence. Good, so that's definitely needed. What else? Yep, so AO is congruent BO, because those are, by definition, of a circle. Yeah. Okay, they're congruent to each other. I'll put the marking in there. Okay, by hypotenuse leg. So those two triangles are right triangles. And we have a hypotenuse congruent to hypotenuse and a leg congruent to a leg. And the hypotenuse leg congruence theorem allows us to say the triangles are congruent. And so then we can, from there, we can say, well, then the pieces must be congruent by CPCTC. Okay. But remember what this theorem's saying. Remember what we started with. A diameter perpendicular to a chord bisects the chord. What if I don't start with a diameter? What if I say, okay, I have a chord here, AB, and I say my radius is perpendicular to the chord? Does it still bisect it? Could it not, though? Well, wouldn't the same argument work if I did this? This is congruent to this. This is congruent to itself. Hypotenuse leg, right? So we don't need diameter. We could say radius as well. And that will be important to know. Radius or diameter, same thing works. You have your hand up? Okay. 8.4. We need to adjust this. We're not actually trying to show, we're trying to show that the measure of these arcs are congruent, are equal. So let me fix this. So the measure of AC is equal to the measure of BC, and the measure of AD is equal to the measure of BD. And if the measures are equal, then the segments are congruent. So I guess you can go either way, but it's important that you know the measures are equal. So a diameter perpendicular to a chord bisects the arcs. And again, let's put the measure of the arcs formed by the chord. Okay, so I'm going to just adjust that a little bit. And so we kind of start with the same idea. We have the circle with this diameter. C, O is the center, here's D. And perpendicular to a chord. Here's A, here's B. They're perpendicular. And we want to show that the measure of AC is congruent to the measure of CB. Okay, that's the first part here. Let's go after that one first. That's an easier one, and probably the first one we would want to look at. And then we'll look at the other. Okay. How do we show that two measures are the same? I just gave you a definition of what a measure of an arc is, right? So if you look back at that definition, yeah, you got to look at the central angle. So the measure of, let's say the measure of AC is equal to the measure of what? What angle? It'd be from A to O to C, this angle right here. That angle right there is the measure of AC. And the measure of CB would be this angle right here. So you get the triangles again, and now we're just showing, can we show that those two angles are congruent, right? Because so if I could show that measure of angle AO, let's say this is E here. Is that the other point you're wanting? the measure of AOE is equal to the measure of angle BOE. And that's true if we could show that angle AOE is congruent to angle BOE. And that's going to be true if we could show that the triangle AOE is congruent to triangle BOE. So it all falls back on, can we show that the triangles are congruent? So how do we do that? What do we need? Jonah, give me something that we need. E what? EO is congruent to itself by what? Reflexive property. Good. Chase, give me something else that we need. What? Yep. Definition of the circle, right? Those. Every point on the circle is the same distance from the center. Okay. So why are the triangles congruent then? Hypotenuse leg, just like the last one, right? And then we can say that the angles are congruent by CP, CTC. And then we can say that the measure of the angles are congruent, or sorry, are equal by definition of congruence. And then we can say that the measure of the arcs are the same by definition of a measure of an arc. Okay. So now if we establish that those two central angles are the same, can you see an argument for why these two angles would be the same? Like, for example, if this was 30 degrees and this was 30 degrees, could you tell me what the other two would have to be? This would be 150. How'd you get 150? They're a linear pair, right? The two angles form a linear pair because they're supplementary. Right? A linear pair is supplementary, and so we can have some kind of argument that says, well, if those two angles are 30 degrees or are congruent, the two smaller angles are congruent, and the two larger angles have to be congruent, which means that the major arcs would have to be congruent, and the measure of those major arcs would have to be congruent. Okay. All right, another statement we need to know is theorem 8.5. If two chords of a circle are congruent, then they are equidistant, the same distance from the center of the circle. So we start with this circle. We have a chord AB. We have another chord CD. Here's the center. And remember, the distance from a point to a line is always perpendicular to that line. That's the shortest distance. So if I want to find the distance from the center to AB, I'm looking at a segment perpendicular to AB. And the distance from that center to CD is also going to be this distance perpendicular to here. And so what we need to show is that if two chords are equidistant from the center, so if this distance here is the same as this distance here, if two chords of a circle are congruent, I'm sorry, no, we don't know that yet. We want to show that. We know the two chords are congruent. I read it wrong. So we know these two chords are the same length. We want to show that the distance between the center is the same. And so you could see if you look at the picture that was given to us, they give us a hint. They say, okay, let's look at a piece of these triangles here. Okay, and let's see if we can show these triangles are congruent, and then maybe we can get these distances are the same. Now they're both right triangles, and what else can we get? Why would they be congruent? We know that this the radius is the same as the radius here. The distance from D to O is the same as the distance from B to O. Definition of a circle. What else do we know? Why is triangle, let's call this point F here, point E. Why is triangle FOD congruent to triangle EOB? Anybody know? They are both right triangles, but we don't know about the other angles. Yeah. I have a hypotenuse congruent to hypotenuse, but I don't have the leg. These we don't know these yet. We don't know leg congruent to leg yet. We'd like to show that, so we don't have that yet. I marked it, so it may be misleading. Definition of circle. What do you mean? Okay, so we already got that. OD is congruent to OB. Yeah. We'd like to show that. Okay, let me give you a hint, guys. FD is going to be congruent to EB for a reason. Anybody tell me why? Good job. So she's pulling back from theorem 8.3. Okay, so this is why we need to know these now, because it's starting to build some theory here. So if it's perpendicular, it cuts it in half, right? And so that's what we have here. These are perpendicular. If CD is the same as AB and they're both cut in half, then the half lengths would be the same as well. Okay, and so FD's got to be the same as EB, and then we can say these are congruent by hypotenuse leg. Okay. And then once we have that they're congruent, we could say that this is true by CP/CTC. Okay. That was a little more thought on that one. Yeah. What's that? Why is FD congruent to EB? Okay, so it starts with AB is congruent to CD. That's given. And therefore the lengths are equal. The measure of AB is, or the length of AB is equal to the length of CD. Well, the reason would be definition of congruence. And then you'd cut them both in half, divide them both by 2. And so those got to be equal, and then you can say they're congruent by definition of congruence again. All right, last one that we want to look at and need to know for this section is that if two chords of a circle are equidistant, it's the converse here, equidistant from the center, then the chords are congruent. So you have this circle, you have two chords, and we know that the distance from the center, right, is always perpendicular. And if those two distances are the same, then those chord lengths have to be the same. Well, again, let's try to show two triangles the same. So if I look at this triangle here, show it's congruent to this triangle here. I'm going to draw it a little differently than what we have over in the picture, but I'll label it in a similar way. So this is O. Let's make this F and D. This is C. Now let's make this B here. I'm going to turn it around a little bit. Put A over here, and this will be E. Okay. So we could say that BO is congruent to OD because of what? Definition of a circle. Okay, they're both a radius. We know that EO and OF are equidistant. What I don't know, actually, I drew something on here that I don't know, right? Or yes, I do know. I do know. They do form a right angle because that's the shortest distance. So those are both right triangles. So actually, this one's a little easier. We already know that triangles are congruent by what? Triangles congruent by side what? No, we don't have this third side. We don't have the third side. But we know we have it by hypotenuse leg. Okay. And so because after that, where would we go? What do we need to show? We can't go directly here because AB is not part of the triangle, right? So what would be the next step? So we'd say BE is going to be congruent to FG by CPCTC. Okay, and then we'd have to talk about. We know that this length is the same as this length, right? We can use a theorem up here. Theorem. Talk about up here, right? Where the if it's perpendicular, it's going to bisect it, and then we can talk about, well, since these are congruent, then you double it, then we're going to get congruent chords. Okay. All right. Turn to your other packet. A couple pages in. Looks like this. Okay. And this is going to summarize kind of what we've been saying. So we're going to fill this in based on those definitions. So two chords are congruent if and only if. We're just proving this. Their corresponding arc measures are congruent.